All right, good day, everyone. So the story here is about waves. And waves are ubiquitous, they're everywhere. You can think definitely of sound waves. That's how you're hearing me right now. Your speakers are producing these vibrations in air that are reaching your ear. These are called sound waves. We'll talk about that later in the course. There are um, water waves, obviously, so that's energy that is being transferred in the ocean via these waves. Light, of course, is a wave. It's an electromagnetic wave. We'll talk about that later in the course and so on. So what is the classification of a wave? What can I call a wave? If I just want to think about the properties of waves. Well, it turns out that anything that is a traveling disturbance could be called a wave. We typically think of periodic things as waves, but in general, any traveling disturbance, you cause a disturbance somewhere and it travels to another point in space, we call that a wave, as long as it carries energy from the original spot to the new spot. So if energy is spreading, energy is being transferred via a disturbance in some medium sometimes, or in some physical manifestation of things, then that's called a wave. So wave is a traveling disturbance that carries energy from place to place. So, for example, suppose I think about something like this. Here's a string of balls that are attached to each other, and then I cause a disturbance here somewhere, and that disturbance travels from place to place and carries that energy with it. Then that's called a wave. Right? Your typical wave that you think of is something like this, but that's more of a periodic wave, we call it. Okay. So there are two really classifications in general about wave. And they talk about the direction of the disturbance and how it's related to the direction of the propagation of the wave. So let's think about this story, for example. Suppose I have a slinky like this, and I'm holding one end of the slinky and the other end is tied to a door or a wall, or somebody else is holding it or something like that. Now, suppose that I start by moving my hand in the same direction as the slinky, right? So I compress some region here at the point next to where I'm holding the slinky. And then I return it back to its position. So this compressed region now is going to travel along this direction. The compressed region is going to keep traveling along this direction. And then after that, there's going to be a stretched region, and then you'll get compressed region, stretched region, compressed region, stretched region, and so on. So that's a wave that is traveling in this direction. If you focus, obviously, this ring here at the beginning of the slinky is not itself traveling. What is traveling is the disturbance in it. Its motion is traveling. But the single loop in the slinky itself is not traveling along the direction of the propagation of the wave. But how is it moving? How is each one of these rings of the slinky moving? It's moving back and forth like this. If you look at figure part C in that figure, and you see each one of these rings is oscillating back and forth along the same direction of the propagation. And we call that a longitudinal wave. As opposed to something that looks like this, for example. Suppose instead of moving my hand in and out, I'm actually moving my hand up and down. In which case, the disturbance that is happening is in the direction perpendicular to the direction of the propagation of the wave. So if you look at each one of these rings in the slinky, it looks like it's oscillating up and down compared to the direction of motion, which is left to right, and we call that a transverse wave. So if I go back to the previous one, the longitudinal waves means that the direction of the disturbance is in the same direction as the propagation of the wave. But for a transverse wave, the direction of the disturbance is perpendicular to the direction of the propagation of wave. So if you think about a wave that looks like this with the balls here, and I just cause a disturbance perpendicular to the direction of the propagation of the wave is traveling horizontally, but I'm making this disturbance here in a vertical direction, then that's called a transverse wave. Okay? So that's an important distinction to make between the two kinds of phenomena, waves that are longitudinal waves and waves that are transverse waves, depending on the direction of the oscillation and the relative direction between that and the direction of the propagation of the wave. Now, if I move my hand back and forth in a periodic fashion, meaning it repeats, periodic means it repeats patterns that repeat every so often. So if I keep moving my hand back and forth, moving my hand back and forth, or up and down, then I create a periodic wave. Periodic wave means that it repeats itself after a certain amount of time. Now, the next slide is really the most important slide in the conversation about waves, because it really tells you about the physical properties of waves that you really need to pay attention to. And what you'll see here in this figure, it looks like two figures here that are identical or close to each other, but in fact, these are completely different stories here on the left and the right. We're going to go back to the waves on a string story here. What I want you to think about is, I want you to think about just one of the green balls here. You say, what does the motion of that green ball look like? Well, it looks like it goes to some extreme position here, and then it passes back through what we call the equilibrium position when nothing was happening. Right? So if I start, this is the equilibrium position of that green ball. And if I start the periodic wave, this green ball oscillates about that equilibrium position as time goes by. So this is at a specific location, and I'm looking at the disturbance as it happens as time goes by. Yeah. This is that figure here on the right at a particular location, and I'm looking at the vertical position as a function of time. Okay, so it's the oscillations here are a function of time at a particular location. I'm looking at one of the green balls, and I'm looking at what's happening to the disturbance as a function of time. The amount of time of one cycle, so from the green ball being at the equilibrium position and then going to the maximum position, back to equilibrium, all the way to the opposite side of the maximum position, and then back to equilibrium, that cycle is called one cycle, and the time of one cycle is called the period. So the period is the time required to complete to one cycle. That's called the period. And remember that happens at a particular location. The maximum position away from the equilibrium position, that's called the amplitude of the disturbance. The amplitude of the wave is the maximum possible disturbance away from the equilibrium position. That's called the amplitude. Now, the thing on the left here, the figure on the left, is a snapshot at a particular point in time. So if I think back about that string of balls on a string and they're performing that wave, if I freeze it at one point in time and I take a picture of that, that's the figure on the left here. So that's at a particular time. And at a particular time, if I look at the length of a wave, because that's in front of me, it's spread out in front of me in space, then the length of one cycle, that's called the wavelength. And again, of course, the maximum disturbance away from the equilibrium position is called the amplitude. Okay, so let's summarize this. The amplitude is the maximum disturbance from the undisturbed position or the equilibrium position. The wavelength is the length of one cycle of the wave at a particular point in time if I freeze that wave and I take a look at it. Imagine with me, for example, a wave in a sports stadium, right? So this wave is going around in the stadium, you know, people standing up and down, raising their arms and then sitting down and so on. Imagine one of those waves. And then you say, if I just focus on one of the people and I look at what they're doing, as time goes by, they're going up and down, up and down. That's the figure on the right. That's at a particular location. I'm looking at a person going up and down, up and down. The picture on the left is of the whole stadium when I fix it at one particular point in time, and I take a picture of that. And I see, you know, one person is standing up, one person is sitting down, etc. And I look for one cycle of that, and that's called the wavelength, because obviously I'm looking at a length. I'm looking at a distance in space. Okay, so I hope it's really clear what the difference between the wavelength is and what the period is. The wavelength is the length of one cycle if I freeze that wave in time. The period is the time of one cycle if I look at a specific location and I look at the disturbance as it repeats itself. There is some time information called the frequency, and that's because it's time information, then it would be related to the period. And turns out the frequency is exactly 1 over the period. So for example, suppose the period takes 1 second, so it takes 1 second to repeat the one cycle. So then the frequency would be 1 over 1 second, so be 1 cycle per second. That's called the hertz. Unit of hertz, hertz is how many cycles per second. Suppose the period was 2 seconds. That means the cycle repeats every 2 seconds. So that means I can have half a cycle every second. That's the frequency. Suppose the cycle repeats every half a second, then I could have 2 cycles every second. So the frequency would be 1 over the period all the time, and it has units of hertz. The light, for example, most lights that are connected to homes, because your power supply that is coming in is about 60 hertz. So that means the lights for you would be flickering at 60 times per second, but of course your eyes can't see that because your eyes are much slower than that. So the frequency in this case would be 60 hertz of the light flickering, but the frequency of your eye taking pictures is much, much slower than that. So that's why you don't see the light flickering and you see some sort of average. Okay, so I'm just trying to explain what the hertz means. Now, it turns out that these two pieces of information are related to each other in a very nice way. The information about the length and the information about the time. So space and time. Now, if you remember space and time in physics 1, they were related by the velocity. And that's exactly what happens here, is that if you think about the velocity of a wave, it's always equal to the frequency of the wave times the wavelength of that wave. That's always the case. The velocity of any propagating wave is equal to the frequency of the wave times the wavelength of the wave. That's always the case. And remember that that's the velocity of the propagation of the wave. That's how fast the wave is going, for example, from left to right. So if I go back to that string and I look at the velocity of the propagation of the wave, that's how fast the wave is going towards the right. See, if I follow that peak like this, moving to the right like that, that's the velocity of the wave. That is not the same as the velocity of a particle attached to the wave. If I look at the green ball seems to be slowing down, speeding up, slowing down, speeding up, while the wave moving to the right seems to be moving to the right at a constant velocity. But a particle attached to the wave has a velocity profile that has nothing to do with the velocity of the wave that is propagating to the right. So these are two things that you got to differentiate between: the velocity of the wave, which is the frequency times the wavelength, and the velocity of a particle attached to the wave. And that's a harmonic motion. That's just, it speeds up, it slows down, it speeds up, it slows down. Okay. Now, if you know two of these three variables, you can find the third. So if you know the frequency and the wavelength, you can find the speed of the wave. If you know the speed and the frequency, you can find the wavelength. If you know the speed and the wavelength, you can find the frequency. Here's a quick example. If you think about radio waves, there are multiple kinds of radio waves. We'll talk about AM and FM when we talk about electromagnetic waves later in the course, but they're basically transverse waves of disturbances in the electromagnetic field. It's okay, we'll talk about this later in the course. But what you need to know for this problem is that the disturbances travel at 300 million meters every second. Now, suppose that a station broadcasts AM radio waves whose frequencies is this much in hertz, and a different radio wave whose frequency is different. Question is, find the distance between adjacent crests in each wave. Distance between adjacent crests, that's the wavelength, because that's the distance of one cycle. So I want to find the wavelength of each one of these waves, knowing that both of their speeds is 300 millimeters a second, but one of them has a frequency of this and the other one has a frequency of that. So I can start out by saying, you know what, I know that the speed is equal to the frequency times the wavelength. So if I know the speed and the frequency, I should be able to find the wavelength like this. So the speed is equal to the frequency times the wavelength. If I want to find the wavelength, divide both sides by the frequency. So I get speed divided by the frequency. That gives me how big the wavelength is. Turns out that for AM waves, it's really, really long. It's 240 meters. That's 2.5 football fields. A really long wave. So between adjacent crests, if I take a snapshot in time and I look between adjacent crests of that wave, the distance between them would be 2.5 football fields, while for FM waves, because they're much higher frequency, they have a shorter wavelength at about 3 meters, which is quite small, like 10 feet, okay, compared to the other one. And of course, if they have a bigger frequency, then they would have an even shorter wavelength and so on, okay? So, and this is true for any kind of wave. Right? The frequency times the wavelength is always going to give me the speed of that wave. That's always true. Okay. Now, there are a couple more things that I want to mention to you in this video here quickly. One of them is about how to figure out the speed of a wave of a string that is under tension. Let's say a guitar string or any kind of string that is under tension means it's there's a force that keeps it tense. And I want to find out how fast waves can travel on that. And it's a really simple story here. It says, if you know how big the tension force is, and you know the mass per unit length, which is called the linear density of the string, the mass for every meter of that string, that's called the linear density. Take the square root of the tension divided by the linear density, you get the velocity, or you get the speed of the wave on a string. And it's kind of intuitive. You can think about it this way. And it really, this intuition should help you with thinking about waves in general. One way you can think about it is that there are two things that are determining the speed. The connection between adjacent portions of that string, so how well they're connected, and that depends on the tension. The more tension you put on that string, the better they're connected to each other. The more, if one of them reacts, the other one reacts right away. So there is this connection between them that is very strong because of that tension that you put across them. The other thing that affects how fast the wave is going is when you apply a force to something, how fast it reacts or how much it actually resists the motion. So the mass of the rope would resist the motion. The more massive the rope is or the string is, the more it's going to resist your attempt to change its motion. So if you increase the tension, you increase the connection between things. So that means that the wave can travel faster. But if you increase the mass of the string, then that means that you're increasing the resistance to any attempt to move it. So that means that the speed is going to be slower on the string. The one last thing I wanted to mention in this conversation is this piece about how can you write mathematically, how can you write a wave? And this is called the mathematical description of a wave or the mathematical expression of a wave. You can always write the disturbance as a function of some time t and some position x. So you give me what position you want to know what the disturbance is and at what time, and I'll tell you what the disturbance is, right? You're looking at a wave on the surface of the ocean and you say, at this point, at that particular moment in time, what is the disturbance? You can find it from this equation. You put the time in, you put the position in, you find the disturbance. So these are called independent variables, the x and the t here. So any equation that you write that describes a wave better have an x and a t in it, because you have to tell me what the position is and what the time is. If you don't know what the position is and the time is, you leave them as variables. And that describes the overall wave, not just the disturbance at that particular location in time. So the equation that the two equations you're seeing in front of you are two equations that describe waves, The top one describes a wave that is moving in the positive x direction, and this one describes a wave that is moving in the negative x direction. You can see the only difference between them is this sign here. But the information about the wave is in this equation here. First of all, A represents the amplitude. That's the maximum excursion from the equilibrium position. If you think about a pendulum, for example, how far does the pendulum swing away from a location and then come back all the way? Or if you think about a buoy bobbing up and down on a wave of water as the water is going across, the buoy starts out, if the water is flat, then that's the equilibrium position. Now the wave comes in, it pushes the buoy up. The maximum excursion from that equilibrium position is called the amplitude. And then 2 pi, of course, because it's a cyclical thing. And f is the frequency of the wave, which is 1 over the period. So that's time information, and therefore it's associated with the time variable here, because the frequency, of course, is time information. It's about how many cycles every second. And then I get, again, 2 pi over lambda, where lambda is the wavelength. And that's associated with the position store. So that's called the mathematical description of the wave.